kind introduction. And also thank you all of you being here. And I'm glad to share our research with all of you today. Okay, today I'm going to present about the bridge rating with the consideration for fatigue damage effect from the truck overload. This is a table of contents for the presentation. First, I'm going to introduce a background of this research briefly, which is the fatigue, and then talk about the introduction and methodology of this study. After that, I will give you some examples to show the effect of this research in practice, and then conclusion. First, I will talk about the fatigue briefly. So I'm pretty sure most of you already know about the fatigue. So I would like to introduce the concept of the fatigue a little bit to remind you before taking up the main subject. So what is the fatigue? When the material is subjected to a repeated load, damages in the material gradually accumulate. So the process where this phenomenon is we call the fatigue. Although the fatigue occurs in any material, its implication has especially been in the metal. So in general, the fatigue is the process of the crack growth in the metal. In the metal, initially there are many microscopic crack scatters. So the application of the cyclic load triggers these cracks and cause them to grow. With the right condition for the metal, a crack will find a path and keeps on growing until it passes through the material effective cross-section and causes failure. It seemed logical to believe that the growth and the final crack paths are random. So however, certain conditions are especially ideal to trigger unexpected path for the crack. So the representative conditions to predict the path are described in the slide. Especially the last one, the welded connection, which is considered in this study, is one of the critical fatigue details. So there are two types of the fatigue damage, the low cycle and the high cycle fatigue. High cycle fatigue occur under low stress levels. This means the stress is sufficiently low such that there is no permanent deformation in the material. Therefore, the failure is by the crack development and growth. So each cycle of the load is believed to cause an infinitesimally small amount of the damage in the material. And the total number of cycles needed to cause the failure depends on the mainly the intensity of the applied stress range. On the other hand, for the larger the stress ranges, the lower the number of cycles required to cause the failure. So the another type of the fatigue damage, which is the low cycle fatigue. It occurs when there are only a few loading cycles that stress the material into and beyond the yield. So each loading cycle will result in a certain amount of the permanent damage in the material. So its failure occurs when the total accumulated damage exceeds the ultimate strain capacity of the material. So usually this type of the fatigue failure, the low cycle fatigue, does not happen in the bridges under traffic load. However, the potentials for the low cycle fatigue mode of the failure exist in the bridges in the active seismic areas. So in general, for the bridge on the traffic load, it is the type of the high cycle fatigue damage. So the fatigue damage in the pavements and the bridges grow more rapidly at the higher load. As the number of requests for the permit to use the bridges by heavy truck increases, there is a concern over the potentials for the fatigue damage from the overload to the affected bridges. The fatigue damage potentials may reduce the service life of the affected bridges, and also it results in the costly repair and the replacement. So special attention will need to be paid in regard to the potential for the accelerated fatigue damage due to the truck overload. Therefore, it is necessary to limit the damage and indirectly impose a limit on the number of permits for a given bridge. So according to the NCHRP report, which is the National Cooperative Highway Research Program, the frequency of the overload are consistently growing. The figure represents the number of permits counted annually for overweight and oversized trucks. Please look at the blue line, which is the total number of permits issued. Despite the dip experience during the Great Recession, it shows a 26% almost increase in the total permit issued from 2005 to 2012. Apparently, the overload and their potential for the accelerated fatigue damage have to be considered in the bridge assessment and also management. Note that the overload used in this research refers to the truck weight in excess of the 80 kits limit, which is like a 356 kilonewton. Therefore, the objective of this research is to determine the significance of the overload in the fatigue damage caused to the bridges, and also develop and calibrate a modified rating equation with the consideration for the fatigue damage potential from the overload. So now I'm going to talk about the truckload population and overload. These are the histogram of annual truck traffic data in terms of the number of axles and the number of classifications. As you can see in the figures, the larger percentage of the truckload population is made up of 5-axle trucks in the vehicle class 9. According to our interest, there are the truckload populations for 5-axle trucks from the weighting motion data. The weighting motion data is collected by the Illinois and Michigan Department of the Transportation from June 2014 to May 2015 for a year of data. As shown in the figures, the populations mostly exhibit an inconsistent pattern with the 2 or more distinct peaks. So this is because of the variety of the load in the population. In other words, the appearance of the 2 peaks may be due to a combination of the loaded and empty trucks in mix. And also the load data contains a frequency of the overload. If we look at the distribution, it shows that the overload are more than 10% of the total truckload population. It is rather large and can be very critical for certain bridges with the critical component prone to the fatigue damage. As I mentioned earlier, generally the fatigue damage in steel structural members of the bridge is caused by cyclic stress range developed as a result of periodic truckload applications. It is mainly affected by the load intensity and the frequency of the stress range at the critical component. In this study, we are especially focusing on the damage that can occur to bridge due to the truck overload. So the service life of the affected bridge will shorten when the fatigue damage due to the overload becomes significant. So how can we compute the fatigue damages? The fatigue damage can be determined by using the minor rule and the SN relation. So for the damage accumulation, we compute the ratio of the applied to the available, the number of the cycles, and then sum up those ratios. For the available number of cycles, it can be determined from the SN relationship curve. This is the SN curve in the H2 specification for fatigue detail categories A through the E prime. In this study, we are focusing on the fatigue detail category E and E prime, and the figure shows the steel beam with welded cover plate, the corresponding to the fatigue detail category E and E prime. Of course, an occasional passage of the overload may not impose any significant amount of the damage to the bridge. However, a repeated application of the overload may result in a faster rate of the fatigue damage accumulation in critical structural components like the figure shown in the slide. So this figure represents the stress range distribution for a given bridge subjected to the different weighting motion data set. So as expected, it shows two distinct peaks in the result, like the truckload population. So now using the minor rule and SN relation curve with the stress range distribution, the annual fatigue damage due to the truck overload can be estimated, which is fatigue life expanded. We use the FLE for this variable. So as shown in the figure shows the fatigue life expanded from the truck overload in terms of the percentage of the overload in the truckload population, which means if consider 0.07, which means 7% of the overload included in the entire truckload population in that bridge or station. So as is shown in this figure, the relationship between the FLE and the percentage of the overload is almost linear. It may be beneficial to incorporate the FLE, which is a fatigue life expanded, as a parameter in the bridge rating equation to account for the fatigue damage potential from the overload. So now I'm going to introduce the bridge load rating. For the overloaded truck, highway agency use a rating equation and conduct a structural analysis to issue a special permit. So it is used in determining the load rating for each component and connection subjected to a single force effect, such as the axial force, flexural, shear, etc. And also it is used by the bridge engineers to determine whether a bridge is okay to carry the applied load or not. So this is the current bridge rating equation in the H2 manual for bridge evaluation. The rating factor can be calculated by the subtracting the deadload effect from the deadload effect from the capacity of the bridge component, and then divide by the live load effect. The equation is following the philosophy of the LRFR method, which is the load and resistance factor rating. For the purpose of the permit load rating, the rating factor represents the safety and the serviceability of a bridge by evaluating the effect of the passage of the truck overload. So generally, the rating of the greater than 1 is considered satisfactory unless otherwise specified. Therefore, we suggest a fatigue index factor in the rating equation to control the additional fatigue damages from the overload. So this factor is not affect to the conventional rating equation, and this is a kind of additional parameter. So we use the IFFLE to represent the fatigue index factor and to account for the significance of the fatigue damage potential due to the truck overload. Basically, this fatigue index factor is related to the fatigue life expanded, which means that it is mainly the fatigue index factor is mainly affected by the type of the fatigue critical component, stress range from the overload, the number of stress cycles, and also the accumulated damage in the component. These parameters also affect the fatigue life of the bridge, as shown in this equation. The estimated fatigue life can be used as a convenient method for estimating the fatigue index factor IFFLE. And the remaining fatigue life can be determined by the subtracting the current age of the bridge, which is A in the equation, from the fatigue life is Y. So based on the concept aforementioned, such as the fatigue damage, bridge rating, and the fatigue life, the fatigue index factor can be developed through the procedure in the flowchart. So from the database generated for the IFFLE, which is fatigue index factor, we found out that among several parameters, the current age of the bridge, gross vehicle weight, and the percentage of the overload are particularly affecting the fatigue index factor. As an example, this figure shows the one of the generated IFFLE for one value of the percentage of the overload. So its trend represents the higher order polynomial function. So it is too complicated. So we propose the equation of the IFFLE is not a constant value. So this is the generic form of the proposed equation. To simplify that complicated trend of the IFFLE, a bilinear function was selected as a suitable function of the IFFLE. And then that function is split into two linear lines with the common point. So this figure represents the bilinear model of the fatigue index factor for several values of the percentage of the overload. So for example, if considered the current age of the bridge is 50 years, which means that the value of the A is 0.5. And then for the 20% of the overload is a dashed green line. So from this figure, the value of the IFFLE is obtained is approximately like 0.4. So using this, the concept and equation, now I'm going to provide the examples to show the effect of the proposed rating equation with the fatigue index factor. So this is a simply supported steel girder bridge with a welded cover plate corresponding to fatigue detail category E. And we consider two cases of the truckload population. As you can see in the table, the case 1 has lower ADTT than case 2, but the higher the percentage of the overload. So using the equation we proposed, the value of the FFLE is the 0.249 for case 1 and the 0.076 for the case 2. That the value affected by the percentage of the overload and also the number of the ADTT. So the figure shows the results of the rating factor for the two cases. The rating values are satisfactory without the fatigue index factor, which means that use the conventional rating equation. So if the gross vehicle weight is less than 150 for the case 1 and 120 kits for the case 2. However, if considered the fatigue index factor in the rating equation, now the rating factor is less than 1 for at the dose gross vehicle weight for both cases. So, which means that the allowable gross vehicle weight is reduced from the 150 kits to the 120 for the case 1 and 120 kits to the 110 kits for the case 2. It is clearly shows that the use of the fatigue index factor in the rating equation disallowed certain number of the overload for a given bridge. So finally, I'm going to talk about the conclusion and the contribution of this research. First, if no limit on the overload permits are imposed, the fatigue damage due to the overload becomes very significant. So we suggest the modification in the rating equation to control the additional fatigue damage due to the truck overload. So we propose a bilinear function of the current age of the bridge and the percentage of the overload for the fatigue index factor in the rating equation. So if the modified rating equation is used, we expect its contribution and some benefits. So first, it will result in the preventing bridges to experience a shorter service life. And also, it is expected to have major economic benefits to bridge owners by minimizing the need for the early bridge replacement and the frequent repair and the rehabilitation. So at the end of presentation, we appreciate that the assistance provided by the David Thompson of the Illinois and Thomas Forts of the Michigan Department of the Transportation in making the weighting motion data available to our research. Thank you for your attention.
And thank you, Dr. Did you finish? I'm sorry, did I interrupt?
Yeah, I'm finished. This is a little bit short presentation, right?
No, it's all right. I think that for the time being, with all this virtual world and the presentations that we have, where at least I talk for myself, I'm very tired of long presentations and that stuff. This was absolutely perfect. Yeah. So thank you very much, Dr. Yang, for your time. I would like to open the time right now for our guests right in the virtual world. If there's any question that you would like to address Dr. Yang, you can speak up, or you can write down on the chat, and I'll read it, and I'll I'll ask her directly. We'll wait. I have a couple of questions for you, but we'll just wait for people to see if they want to ask anything particular.
Sure.
Let me see if I'm having her here. All right. Well, apparently they're apparently it was so clear, or maybe they're a little bit shy. We'll see. We'll see what's the reality. I'm going to ask a couple of questions. It's very interesting how, in a very simple way, with a simple addition of this fatigue life expanded factor, you can modify so much the bridge rating, which is impressive. I mean, of course, it's mathematically speaking, it's expected, but never to be that much in terms of the data that you can collect from a weight in motion test. So the first question that I want to ask you, Dr. Yang, is, you know that currently we are working in with Javeriana University. Oh, there's a question. Well, let me. There's a question on the chat. Oh, okay. Yeah, I'm going to go for our attendees first, and I'll ask. So Professor Gonzalez Sandoval, she asks if this analysis can be applicable for pre-stress bridges.
So far we just consider the steel beam bridges because the fatigue detail is considered, especially the detail E and E prime, like a cover plate. So if you want to adopt this analysis to the pre-stressed bridges, you need to think about what kind of the fatigue detail affect to the bridges, to the fatigue damages, and also if it's not really huge, the damage from the overload to the bridge is not any beneficial to use this analysis.
All right. So to get this correctly and to get it straight, if for some reason we have the SN curve that represents the fatigue life of that pre-stress detail on that bridge, it could be applicable. Am I right, Dr. Yang?
Or I'm sorry, I didn't get you.
Oh, okay. So I'm asking if what you're asking is that if for a reason we get to know the SN curve, you know, the stress a number of cycles curve that represents that pre-stress bridge, it could be applicable as the same way you are doing it for these cover plate bridges. Is it possible?
Yes, that's possible. Well, I need to check if there is any extra parameter we need to consider instead of that parameter I already considered. But theoretically, yeah, you can use that.
Okay, that's excellent, because for this stage of the research we're doing right now, we would like to consider it right now, because Colombia has a lot of concrete, reinforced concrete, and post-tension and pre-stress bridges. So it might be 100% applicable. Not for what we're doing right now. We don't want to redo the whole thing, but it could be a new line of research applying what you have right now, which makes it absolutely interesting. What I wanted to ask you in the beginning is if we wanted to evaluate then this FLE factor, first step would be to have a good traffic characterization to see how that correlates with the overloads. Is that right? Am I correct?
Yes, I tried to provide that. Hold on, maybe I can show you this figure. You're talking about this one, right?
Right. I mean, you did this for, I think the data you took belongs to Michigan State Department of Transportation. or Illinois Department of Transportation, which is very convenient. We would like to do this from zero, from scratch here in our country. So what would it be that first step to get that graph that you have right now? What would be your best, your suggestion, the first step we should do?
Okay, to obtain this fatigue life expanded graph for, just ignore the other bridges. It's considered just one bridge. You can see the let's say the rectangular one. There is some different spot, right? Mm-hmm. That represents for the results of the each different weighting motion data set, like, which means the different location. So first, you need to find what kind of the truckload population is in your the location, mm-hmm. and then compute the conduct a structural analysis corresponding to each the truckload, and then using the this minor rule, and then you can determine what is the applied the cyclic applied load to that bridges, and then you can determine what is the available, the number of cycles, and then determine the minor index, like a damage. As you can see, the number of the damages is very low because I didn't consider the the damage from the under the 80 kips truck in this graph. So extracted the damage from the overload, and then combine the percentage overload in that specific
okay.
to the location.
Okay, I understand that. Another question that comes to my mind just because of what you said: for how long? I mean, what was the period of time that these data covered doing truck check with the weighting motion? How long was it? Is it 1 week enough? Maybe a month it's too long? How many days should I do this outside to have a reliable number of data truck passes so I can start doing my calculations and then compute the it's called the fatigue life expanded?
Right. We consider actually a year of the data because in general a year has a 4 seasons, right? 4 terms. So each term, like a summer or spring, you guys have so many construction. You may have the more the overload truck than the other period, like a winter, right? Mm-hmm. So to consider those kind of parameters affect to the trend of the truckload distribution, you need to consider at least a year of the data. Then additionally, I didn't mention in this presentation, but you need to consider traffic growth rate, like a 2% or 3% annually, something like that. And then you can develop the more specific truckload distribution.
Okay, that's a wonderful.
Sometimes, yeah.
It's a wonderful answer. It's just a complication for us. 1 year, it's going to make it a little complex.
Because 1 year can be represented the 2 year and 3 year around that, like from 2012 to 2015. That you can represent just 1 year from those periods.
Okay. Okay, very interesting. I'll take this to the guys in control of this, so they'll see for how long is that we have to do this. They're not going to like it. It's just a little
actually,
too much.
We already did for this some research before this determining the fatigue index factor. we developed the theoretical torque load distribution for example, when you don't have the weighting motion data enough, so you can predict what is the possible torque load distribution. Of course, that's gonna be the conservative, right? But at least you can predict some fatigue damage for the future.
Okay, yeah, that's right. You're right. One last question. Let me check.
Okay.
One last question that I have, Dr. Yang, is can you go to the example curves where you have the relationship between the FLE and the I think it's the gross vehicle weight. So this graph was done applying the methodology to a real bridge, right?
Yes.
Okay. No,
Essentially supported beam bridge.
Okay. In this bridge was steel girder with a cover plate and a concrete slab on the upper part.
Right.
All right. Okay, that makes sense. And we can apply it. We have a couple of bridges in here that we can still apply it to. And no, that was my question. Like my question was like, has it been tested to a real bridge, and then how big is the impact in terms of the bridge rating? And there's the Dr. Consuegra has a question. Yes, sir. I'm reading. If you okay. It's the room is yours, Professor. You are free to ask.
Yeah, I just realized that I have the capability of opening my microphone on myself. So
that's
okay,
good.
That I didn't open up the microphone when I was doing something else here in the room. So
good to know.
Yeah. Question, Dr. Jan, thank you for presentation. Very interesting and very nicely short presentation, which, as the professor just said, is very appreciated. We are very tired of very long presentations, and very often it's more important or it's better to have like a very concise presentation. I wanted to ask you something. I'm not a very steel guy.
Oh, okay.
Probably more into the concrete guy, even though very often we get to design steel bridges in the company. But I'm still curious about something. As far as I understand, fatigue is a problem or a phenomenon that is based on basically this type of information plotted in an SN curve, right? Which is based on experimental observations, on numbers that are being measure. I mean, the stress level related to the number of cycles in the real number of cycles, sort of speaking, in the structural steel. I wonder, because I made the comparison with concrete, and I know very well that concrete fatigue phenomenon is not just an unknown phenomenon, or is at least is not that much known as it is in steel. But I'm curious about to know if at this point, based on information or the knowledge that we have right now in structural engineering, do we feel comfortable, or how confident are we, or we are about these SN curves for the steel as a material, understanding material that is very homogeneous, and the type of material that we believe is more understood than the concrete. Just to make it right to the point, my question: do we have right now enough information to be confident about the SN curves for any kind of steel, at least the type of steel that we use for bridges, or our research continue to be based in highly proportion on experimental data to recreate the SN curves? I don't know if I'm making myself clear.
At first, thank you for your kind words. And then, if my understanding is correct, you want to ask me the current SN curve is reliable, right? For the steel.
Yes. Yeah.
Okay. How can I say this? So far, the AASHTO also adopted this SN curve, and also many areas use that SN curve, but this is not the materialized. That's the type of the fatigue detail. Like, for example, the bolting is much stronger than the welding in terms of the fatigue, right? So that one is developed by the type of the connection or some connection or the detail, not the material type.
I understand. Just
Yeah,
about
so,
the material only, but about the connection or the bolting or
sure,
the.
that is a more important factor in the SN curve.
I
So
see.
that's why we consider the E type E and E prime instead of the A and B. And also, if you consider the information from the FRA, Federal Highway Association, we are focusing on the. Can you see my cursor?
Yes.
No. Okay. This area, approximately, this area is more critical to the fatigue damage. The above the line, like A, B, and this area, we may don't see in reality the kind of the fatigue damage or fatigue failure. So, which means that graph is developed for the steel fatigue detail, but the critical part is related to the type of the detail, not the material one.
Okay, I understand. Thank you very much.
Yeah.
Okay, and I would like to complement what Dr. Yang said to answer Dr. Consuegra as well, is that back in the 70s, the University of Illinois and Texas Department of Transportation, Washington Department of Transportation, and if I am not wrong, the California Transportation Department as well, they invested something impressive. I'm talking about $1 billion testing all these type of elements, and then people got tired of doing these tests because they already. I mean, a fatigue test is horrible. It takes about a year. It takes about 2 years. If you're going into the high cycle fatigue, it can take 5-7 years with no problem, and nobody wants to go over there. I mean, someone died over there in the labs reporting these curves. Okay, that's it. I mean, someone already did it. However, due to new construction elements, connections, technology, weldment qualities, and all that type of stuff, certain structural elements push a little bit this boundary, and they force researchers or the departments of transportation of the bridge offices of the different countries to create their own tests. And it is a continuous line of research, Dr. Consuegra.
Oh, sure.
I see, and I believe you. I remember very well when I was in school and having friends and colleagues in the lab coming into the lab very late in the night. You know, like at the midnight, going to that they were testing with the lighting and to look for cracks, and it was so amazing because they had to do that very often and very unusual hours. And as you say, this is something that you need to turn on the machine and do a lot of cycles and come back in a few millions of cycles and check and go back again in a few more, and it is not only expensive, but it needs a lot of effort and patience.
Yeah, it's boring.
Also, this graph is categorizes the details, not the specific to the detail, like A to E prime, right? So, and also this one is a probabilistic method, not the exact value from the experiment. So when they do test for the new connection for the consider this effect, they just look at okay, this stress level is enough to show the relation between the stress range and the number of cycles. They will put that new connection in one of the categories, not the change that category. But I saw some researcher try to modify the SN curve, but that depends on what kind of structure or system. For the bridge, it is very huge, right? But if you consider the mechanical engineering, like actually I'm working on the wheel life, the development of the wheel life in railway. So if you consider that the SN curve for that material, that's a little bit different with this SN curve, but that's affected also the different way. The behavior is different.
I see. Well, thank you very much.
Thank you.
Okay, so I want to ask, we have 4 minutes before time is over. Is there any other question on the room? Okay. Well, Dr. Yang, thank you very much for your time. I personally enjoyed this work a lot because that's part of my life right now. And I spent it a lot of years, like Dr. Consuegra said, in a lab. I was that guy at night coming. I had a cushion next to the fatigue living, that was me. And I really find fascinating how with a nonlinear equation like this, you can affect so much the impact gradient, which is, it's not a simple thing to do. I mean, not every day you have someone that changes the equation of fatigue rating for a bridge according to the AASHTO standard. So I really hope that this presentation that you did today for Javeriana guests, and I want to thank everyone presenter right here. But I really expect that this was just the beginning of a very, very extremely long research communication between you and Javeriana University. And I would also like to invite you in the future when we can take an airplane again with safety and without this bio problem that we have right now with the COVID-19. So you can please come to Javeriana University here in Colombia so we can exchange information and so you can get to know a little better about us.
Thank you for saying like that. And if you have any further questions, just send me email. I can try to do my best to answer.
Okay, that's very kind of you. Thank you very much. So thank you very much, everyone. And this is it, the end of the seminar series. Thanks for your attention, and thank you, Dr. Yang. Have a good day, everyone.
Thank you.
Thank you. Have a good day.
Thank you.
Have a good day.
Bye. Thank you very much for your time here. All right. But that was really awesome, Bora. I have to say thank you very much for your time. And
thank you. I really enjoyed the conversation.
Yes. I mean, fatigue is such a great topic. I guess this is like an acquired taste. You don't really get to love it right now, but I really enjoy it. I mean, it's impressive. I really like it. And I want to know how we can apply this for further research, and not only for those horrible E and E prime categories for the AASHTO world, which you don't want to see those things in the world, but how is it going to be affecting the other ones? I would like to see that. But for now, I'll let you go to have lunch. Thank you very much for your time, Bora.
Thank you very much. Bye.
Okay, bye-bye.